A buffer solution is a weak acid and a salt of its conjugate base, or a weak base and a salt of its conjugate acid. Buffer solutions absorb hydrogen ions or hydroxide ions that are added to it and therefore resist changes in pH. So in this particular problem, we're going to make a buffer solution that contains sodium cyanide and hydrocyanic acid in solution, and we're going to calculate the pH of that buffer solution. Once we do that, we're going to add a strong acid to that buffer solution and see how the pH is affected. So in our first step, we want to calculate the pH of the buffer solution. And to do that, we're first going to list the major species that are found in the solution, choose the species that can dominate the reaction by comparing the K values, find the concentrations of all the species involved, and then make our ice chart, write our K expression, solve for X, check the 5% rule, and calculate our pH. So in this particular problem, we have a solution that's prepared by adding 31.56 grams of sodium cyanide and 22.30 grams of hydrocyanic acid to 600 milliliters of water. And it tells us that the Ka for hydrocyanic acid is 6.2 times 10 to the minus 10. So first we want to list the major species that are in the solution. We've got sodium cyanide, and we know that that's going to dissociate into sodium ions and cyanide ions. We've got water, and we've got hydrocyanic acid. Well, water has a K value of 1 times 10 to the minus 14. Hydrocyanic acid has a K value of 6.2 times 10 to the minus 10. And cyanide ion has a Kb value of 1.6 times 10 to the minus 5. And that's determined by taking the Ka and dividing it into Kw. So by looking at those values, we know that the cyanide ion has the largest K value, and that's where our reaction is going to begin. We're going to need to decide what it reacts with, and in this case, it's going to react with the water in the solution to produce hydrocyanic acid and hydroxide ions. We have to calculate the concentration of the hydrocyanic acid and cyanide ion. So if we take 22.30 grams of hydrocyanic acid and convert that to moles and divide it by the volume of the solution, that's going to give us the molarity of the hydrocyanic acid. And then if we take the grams of sodium cyanide and convert that to moles, and for every 1 mole of sodium cyanide, we're going to have 1 mole of cyanide ion, divide that by the volume of the solution, that'll give us the concentration of the cyanide ion, 1.07. So our reaction is going to be the cyanide ion reacting with water to produce hydrocyanic acid and hydroxide ions. So we'll plug in our cyanide ion, 1.07. We'll plug in our hydrocyanic acid, 1.37. We'll fill in our ice chart, write our K expression, plug in our values, and solve for X. And in this case, our X value is going to equal 1.25 times 10 to the minus 5, which is the hydroxide ion concentration in the solution. We can figure out the percent dissociation by taking that 1.25 times 10 to the minus 5, dividing it by 1.07 and multiplying it by 100, and it's definitely less than 5%. If we take the negative log of 1.25 times 10 to the minus 5, that'll give us our POH, and by subtracting that from 14, that'll give us our pH. So this buffer solution has a pH of 9.1. Now what we're going to do is we're going to add 50 milliliters of 3 molar hydrochloric acid to our buffer solution and see how that affects the pH. And again, what we're going to want to do is list the major species that are in the solution, decide what reaction will dominate, and remember that the goal of an acid meeting a base is to neutralize. And then we're going to need to make an ice chart, except that this time we're adding 2 solutions together, so we're not going to be able to use molarities in our ice chart. We're going to have to calculate the moles of all the species that are in the solution, do a mole ice chart, and recalculate our concentrations after that. So let's look at what we have. We have hydrocyanic acid and cyanide ion from the original buffer solution. We're adding hydrochloric acid, which dissociates into hydrogen ions and chloride ions. We always start with the strong acid or the strong base. So the hydrogen ion is going to react with something in that buffer solution to neutralize it. Acids react with bases, and the cyanide ion is our base in our buffer. So the hydrogen ions are going to react with the cyanide ions to produce hydrocyanic acid. So here's our reaction. Now, because we have 2 different solutions, we can't use molarities in our ice chart. We have to use moles. So for our hydrocyanic acid, we're going to take the molarity times the volume, and that's going to give us the number of moles, so 0.822 moles of hydrocyanic acid. We're going to take the concentration of the cyanide ion, multiply it by the volume, and that'll give us the moles of the cyanide ion in our buffer solution, so 0.642 moles. We're going to take the molarity of the hydrochloric acid, multiply it by its volume, and that'll give us the moles of the hydrochloric acid, which equals the moles of the hydrogen ion. We'll plug our values into our ice chart next, so the moles of hydrogen ion are 0.150. The moles of our cyanide ion are 0.642, and the moles of our hydrocyanic acid are 0.822. Strong acids and strong bases react to completion. It's a limiting reactant problem. And in this case, all of our hydrogen ion is going to be consumed, and we're going to be left with cyanide ion and hydrocyanic acid in the solution. So we still have the components of our buffer solution left over after the hydrogen ion has been completely consumed. Next, we need to calculate the concentrations of our cyanide and our hydrocyanic acid left in our solution. But we need to remember that we added 2 solutions together, so our new volume is going to be 600 plus 50 milliliters, or 650 milliliters. So the molarity of our cyanide ion is going to be 0.492 divided by 650, so 0.757 molar. And our hydrocyanic acid is going to be 0.972 divided by 650, which will give us 1.50 molar. But right now, all we have is the cyanide ion and the hydrocyanic acid concentration. And from those, we can't figure out the pH because we need either the hydrogen ion or the hydroxide ion concentration. So we're going to have to go back and do another part of our problem, the equilibrium part of our problem. It's basically the same as what we did at the beginning, where we want to calculate the pH of our buffer that's remaining in the solution. So first we want to list what's left in the solution. We've got the hydrocyanic acid, we've got the cyanide ion, we've got the water, and we've got the chloride ion. Now the chloride ion isn't going to do anything. The hydrogen ion was completely consumed, so it's not there anymore. And we're going to make our new ice chart. So the concentration of our cyanide ion is 0.757. The concentration of our hydrocyanic acid is 1.50. And we don't have any hydroxide ion originally, so we'll put down 0. We'll have a shift towards the right. We'll come up with our equilibrium values. We'll plug them into our K expression. and we'll calculate x. So in this case, x equals 8.1 times 10 to the minus 6, which is our hydroxide ion concentration. Our 5% rule is much less than 5%, so we're okay with assuming x is insignificant. When we calculate the pOH of the solution, we get 5.09, and subtracting that from 14 gives us a pH of 8.91. So if we go back to the beginning of this problem, we calculated the pH of the buffer solution before we added the hydrochloric acid, and we came up with a pH of 9.1. In the next part of our problem, we added 50 milliliters of 3 molar hydrochloric acid. The buffer consumed that strong acid, and the pH only went down to 8.91. So buffers consume hydrogen or hydroxide ions that are added to them and resist changes in pH.